Hi there, my name is Ayush Gupta. I'm a student in Tomas Palacios' group. Unfortunately, he cannot be here today, so he asked me to fill in. And today I'll tell you a little bit about the work that our group is doing on growing and making transistors out of these things called 2D materials, and potentially how they can be used to make circuits for display backplanes. So essentially, a display is just a grid of pixels. Typically, for LEDs, they're just diodes, and then LCDs or liquid crystals, you can model those as capacitors. But most of the displays that we interact with are active matrix displays, which means that each of those pixels is individually driven by a transistor or a simple driver circuit, and which controls the pixel. And you have circuitry on the periphery of digital circuits on the periphery of the display, which interact with the driver circuit, which then sends a large amount of current, or however much current is needed to turn the pixel on or off. So if we zoom into one of those pixel driver circuits, so this is a very simple example with two transistors and a capacitor. So the job of the transistors is to interact with the control circuitry outside of the display and then send current to the diode or to the liquid crystal to turn it on, and then when the control says otherwise, to turn it off. So this is a very simple example for one diode, and you can imagine if you have a full color display, each pixel has an R, G, and a B, and you need to have slightly more and more complicated circuits. So these transistors are typically made, or they're called thin film transistors, or TFTs. And there's currently three main materials that they're made out of: amorphous silicon, low temperature polysilicon, or LTPS, and then amorphous indium gallium zinc oxide, or IGZO. So each of these materials has their advantages and disadvantages. Amorphous silicon is very widely used because it's very cheap to make. The problem is that it has very low electron mobility, which indicates poor material quality. Then you can anneal this amorphous silicon and get something called LTPS. So you can get much better electrical properties out of the material, but it's more complex and expensive to manufacture. And then something that's recently becoming more common is IGZO. So this has a higher electron mobility compared to amorphous silicon, but it's still not as good as LTPS in terms of material properties. So we propose that instead of these three materials, you can also use 2D materials as backplane circuits. So 2D materials are characterized by, they're very atomically thin, so between 1 to 3 atoms thick per monolayer, and they have van der Waals surfaces on or out-of-plane surfaces. So you have covalent in-plane bonding and van der Waals out-of-plane bonding. And they're incredibly diverse, so they have a wide variety of electronic properties. They range from metals, semi-metals, semiconductors, insulators, and superconductors. But our group in particular focuses on two 2D materials in the family of transition metal dichalcogenides, or TMDs. And so the ones that we work on are molybdenum disulfide, MOS2, and tungsten diselenide, WSE2. So these are both semiconductors, and the unique thing is that MOS2 is an intrinsically N-type semiconductor, and WSE2 is an intrinsically ambipolar to P-type semiconductor. So if you look at the material properties of the conventional TFT channel materials and you add 2D materials to the mix, so there's a few key metrics that we want to look at. Primarily electron mobility, deposition temperature, the transistor current on-off ratio, whether it's transparent or not, and then whether you can make a CMOS circuit out of it. So you need to have both N-type and P-type. So if you look, amorphous silicon is pretty poor on all of these metrics, but LTPS and IGZO, they tend to improve. But each of them, they have some positive aspects and then some restrictions. So for example, IGZO, it has reasonable mobility, but it can be deposited at room temperature, and it's very transparent, but you don't have access to P-type transistors. On the other hand, LTPS, it has very good mobility, but it's not transparent, and it's more complex and expensive than amorphous silicon. And we argue that 2D materials, at least for the properties listed here, are pretty good. So they have reasonably high mobilities compared to LTPS. You can deposit them at reasonably low temperatures, but they have good on-off current ratio. They're optically transparent, and you can access both P-type and N-type transistors. So just this here is a plot of mobility on the y-axis versus the number of pixels on a display on the x-axis. And each of those lines represents a particular refresh frequency of the display. So you can see that as you increase the refresh frequency and increase the number of pixels on a display, the required mobility of your backplane TFTs must increase. So having a high mobility with TMDs having a high mobility, that's an inherent material advantage for faster switching and higher pixel density displays. The other advantage of having a higher mobility is that for a given current, you need to apply less voltage to the transistor, and so that corresponds to a lower power consumption. So the other characteristic is a good transistor, when it's on, it needs to be really on, so it needs to have a high current. And when it's off, it needs to have a very small current. And that's one thing that IGZO does very well compared to silicon, because it has a wide band gap. Now, MOS2, for example, it doesn't have as wide of a band gap as IGZO, but its band gap is still roughly more than double that of silicon. So it'll still provide advantages in this regard. And having a very low off current is good for reducing power consumption. The other thing is that because these 2D materials are atomically thin, so device scaling in the vertical and lateral dimensions is linked. So if you scale in the vertical dimension, it's easier to scale in the lateral dimension. So you're able to make transistors that physically take up a smaller area. And then the other advantage, of course, is having access to both N-type and P-type 2D materials. You can make CMOS circuits. So for example, the digital circuitry that's on the periphery controlling the display rather, can also be made with 2D materials. So just a brief outline. First, I'll talk about work that we've already done with low temperature MOS2 growth, and then some work on, or updates on growing TMDs, both N-type and P-type, and then a brief overview of some devices that we've been making. So what we started out by doing was custom making a 10-inch metal organic chemical vapor deposition furnace, or MOCVD, to grow MOS2. And so this is capable of growing MOS2 on 8-inch or 200 millimeter wafers. And it can do it at a low back end of line compatible temperature, 250 to 300 C. And you can grow a monolayer of MOS2 in a relatively short time, less than an hour. And so the way that this furnace works is that you flow your precursors in from the left, and then your wafer is sitting here in the middle, and then on the right is the heating element in the furnace. So these precursors, they actually flow around the wafer, and then they decompose in the heating, near the heating element, and then they flow back and then are deposited onto the wafer. And then so we can perform characterization on these materials that were grown at a wafer scale. And we can see that the growth method is originally they start with these triangular flakes. They nucleate as these triangular flakes. And as you increase the growth time, those triangular flakes grow, and then they merge into a continuous film on the 8-inch wafer. And we can perform some optical characterization on the films across the wafer scale, specifically with Raman spectroscopy and PL or photoluminescence measurements. And we can see that they're pretty uniform across the 8-inch wafer. But then we can fabricate transistors across the wafer, and we see that there's a little more non-uniformity starts to emerge. And using these transistors, we can actually extract the mobility of the material, and it's somewhere on the order of 30 to 35. But the problem here is that there is some variation in the material. And you can see, so these are transfer curves for maybe 100 or so devices, and there is some variation in the electrical characteristics. So what we did was we performed fluid dynamics simulations of the reaction chamber, and we found that by putting a diffuser at the gas inlet, you can actually improve the uniformity of the gas flow throughout the chamber and hopefully produce a more uniform material. And it turns out that that's what happened. So this is a measurement of 100 MOS2 transistors on the 8-inch wafer, showing very good uniform performance. So that's sort of what we've reported previously, and then a little bit about what we've been working on recently. So said before that the mobility that we got originally was around 30 or 35 centimeters squared volt second, but we can do better. So what we've been working on is optimizing the growth parameters to sort of improve the material quality. And the main way, some of the variables that we can play with are the gas flow, the temperature, and how we pre-treat the substrate. And then also, so we use sodium chloride as a seeding promoter for the MOS2, and playing with that concentration is another variable that we can adjust. So yeah, basically the study that we performed recently is we modulated the sodium chloride concentration, and then so you need to balance both how many nuclei you create with the seeding promoter concentration, and then with the growth time. And then so what we get is films, I guess it's a little harder to see here, films that look relatively uniform, and our mobility improved 2 to 3 times to 60 centimeters squared per volt second. And we're able to get mostly monolayer films fully coalesced across a wafer with reduced defect density. And so these are some transfer and output curves from some of the devices that we were able to fabricate from this wafer scale material. And then the next steps are approaching a mobility of around 100 and looking at alternative seeding promoters. And we're also trying to do further material characterization. So the work that I was just mentioned was on silicon substrates, but we're actually also able to grow these materials on flexible substrates. For example, here is polyimide. So there's a picture of the wafer, and then this is, so it's on a silicon backing, but you can also, after the growth is done, remove it. And you can see here the flexible substrate. And we can fabricate devices on the polymer, and they show reasonable performance. So that's for MOS2. We have also started recently the growth of WSE2, which can be used as a P-type material. And this is a lot, we're in the earlier stages of this work, and instead of an 8-inch furnace, we're starting off with a 1-inch furnace. The idea is by optimizing the parameters on a smaller scale, we can learn some valuable lessons before translating it to a wafer scale. So we use tungsten hexacarbonyl and diethyl selenide precursors, and this is an image of the furnace that we're using. And the material that we get, so you can see it's very polycrystalline, and it has triangular-ish flakes. And we've performed material characterization using Raman and photoluminescence spectroscopy, and we can confirm that we successfully synthesized the tungsten diselenide. So moving on from material growth to devices. So the first thing, in order to make a high-performance transistor, you need to do a bit of contact engineering, because contact resistance is one of the main limitations for the performance of a transistor. And we found that using semi-metals as contacts to 2D materials can get you very high-performance transistors. So, for example, these devices have antimony contacts, and they show current densities in excess of 1 milliamp per micron, which is approaching the performance of silicon CMOS transistors. But one channel typically isn't enough, and especially when you're driving a display, you need more current to turn that LED on. So what we found, and one of the advantages of 2D materials is you can actually stack them together to make multiple channels. And so within the same footprint, you can have 2, 3, 4 times the current. So what we've been doing is designing these multi-channel MOS2 transistors using, so this demonstration has 2 channels. And you can see cross-section TEM images might be a little harder to see, where in the gate region, you essentially individually gate each of these 2D layers, but in the contact region at the source and drain, you collapse the 2D layers and make a single contact. And EDS, or energy dispersive X-ray spectroscopy results, confirm the successful fabrication of this structure. And then you can also electrically characterize these double channel transistors. And the main confirmation that these actually worked as designed is compared to a single channel transistor, the current density approximately doubles. And also you can measure the gate capacitance. So if you have 2 channels, then of course the gate capacitance should double compared to a single transistor. And that is what we measure. So we're also thinking not just on a device level, but on a system level. And you can see here on the left is a cross-section of what a display might look like. And so you have many different layers with different types of devices. On the top, you have your LEDs, and on the bottom, you have your transistors. These all need to talk to each other, and they do that with metal interconnects. So one of the other things we've been looking at is the effect of our 2D material growth on these metal interconnects. The main concern is that when you use sulfur as a precursor in MOS2, it can sulfurize the metal and greatly increase the contact resistance. Or not the contact resistance, the sheet resistance. So, for example, you can see the images here. As you increase the time and the temperature that the metal interconnects are exposed to the sulfur environment, they clearly degrade, and the blue plots show that the resistance drastically increases. But we found that by passivating these interconnects with aluminum oxide, you can actually keep roughly constant resistance no matter the time or the temperature. And then just briefly, some initial work on our P-type devices as well. So this is a lot more preliminary, but so P-type devices need very high work function metal or semi-metal contacts. So one of the initial metals that we used as a contact was platinum. And these devices show reasonable P-type performance, but the good thing is that they have a very high yield and they show roughly uniform performance. So just like semi-metal contacts were useful for N-type materials, they can also be useful for P-type materials. And in particular, some 2D semi-metal contacts such as titanium disulfide, vanadium diselenide, also some bulk semi-metals such as tantalum phosphide. But we can compare, we've done some initial work on comparing these semi-metal contacts with conventional palladium and platinum contacts. So this is just some initial devices showing reasonably good on-current densities, but a lot more work needs to be done on contact engineering to make good P-type transistors. These are just output curves also from the same set of devices. So in summary, we've demonstrated low temperature, high quality MOS2 MOCVD growth on an 8-inch wafer. We can do that on silicon oxide or polymer wafers. We have some initial studies on the growth of P-type tungsten diselenide as well as contact engineering. We've made multi-channel MOS2 transistors which allow for increased current density within the same footprint. And then some future work that we want to do, of course, we want to improve the P-type and N-type material quality. We can put those together and make CMOS circuits, integrate those with LED layers. And then so I only talked about 2D materials today, but the other half of our group works on gallium nitride. And so we're thinking about making these display driver circuits with gallium nitride as well. So with that, thank you.
Backplate circuit instead of the point twist, no point setting. Yeah, the consistency
looking for analogies with other semiconductors. Can you dope these?
Yes, you can.
Or do you want to?
Probably, you don't want to substitutionally dope them because that really reduces the mobility. People have been doing a lot of research into charge transfer doping, so putting another layer next to this, and then and that will induce charge carriers without disrupting the crystal structure. So you could do that, but all of the data that I presented was with undoped MOS2 and undoped tungsten diselenide. So it might be helpful to do doping at the contact regions to reduce the contact resistance, but probably not in the channel.
Is it functions of light sensitivity or don't have any autonomous change with the light on, light off?
Yeah, so there is. So actually, one thing that I did not mention was a lot of these TMDs in the single layer limit, they have a direct band gap, so they are optically sensitive. So that is something that a lot of people are working on, but in our group, we just happen to be focusing on the electronic properties instead of the optical.
Okay, again, Tomas, speaker.